Hello and welcome. Thank you for stopping by to check out my research. I will be presenting on solar water splitting for hydrogen production, specifically focusing on the synthesis and characterization of bismuth vanadate. Alright, a little introduction into what we were trying to accomplish through our research. The primary goal of our research was to reliably synthesize bismuth vanadate films. Bismuth vanadate is a N-type semiconductor and a nanoporous material. You can see the structure of it on the right, forming a monoclinic scheelite. This material gives us a lot of promise for sustainable hydrogen production because it has a band gap of about 2.4 eV, which is an ideal band gap to direct water electrolysis. So when films of this material are used as the anode of an electrochemical system, it can split water requiring only sunlight as the input. Our research process can be mainly divided into four distinct parts. Everything began with the electrodeposition of bismuth oxyiodide. Then it was converted to bismuth vanadate through annealing and etching. Afterwards, the films were characterized with X-ray diffraction and a scanning electron microscope. And finally, the bismuth vanadate films were tested in a photoelectrochemical system, but I won't be talking much about this in my presentation as my research partner will be discussing it in further depth. Here is an overview of the electrodeposition process that we carried out. We first made a solution composed of a water-ethanol solvent dissolving the necessary amounts of bismuth nitrate, potassium iodide, and p-benzoquinone. The iodide was particularly an important compound within the solution because it contributed to bismuth stability within the solution. It would form a tetraiodide compound with the bismuth, increasing the solubility of bismuth in the solution, whereas otherwise it would not be very soluble. We then used this solution to electrodeposit bismuth oxyiodide onto FTO films by applying a potential from a potentiostat. P-benzoquinone is the key compound within the solution that supervises the electrodeposition of bismuth oxyiodide. It does this by controlling the pH at the site of the film. When a potential of 0.699 volts is applied, the benzoquinone can undergo reduction to become a more basic compound, hydroquinone, as seen by that reaction in the slide. This increases the pH at the site of the film, which causes the bismuth to precipitate from the solution in the form of bismuth oxyiodide. So these are the resulting films that arose from the electrodeposition. The dark orange is the bismuth oxyiodide on the clear FTO films. Upon producing these films, we had to make sure that the compound was actually bismuth oxyiodide. So we characterized them using X-ray diffraction. As seen in the figure, there were key peaks that indicate bismuth oxyiodide at 2 theta equals 29.7, 31.7, 45.4, and 55.1. When comparing it to some literature, looking at curve A, we can see that the peaks match very well, thus confirming the bismuth oxyiodide. So once we confirm that we have bismuth oxyiodide, we move on to the conversion process where we convert it into bismuth vanadate. The first part of the process is the annealing step. We covered the film surface with vanadium solution, and DMSO was used as the solvent in particular because of its wettability factor, making it easier to spread across the surface evenly. Once the solution was added, as seen in the pictures, it was put in a 400 degrees Celsius furnace. At this temperature, the bismuth oxyiodide decomposes into bismuth oxide. Meanwhile, the vanadium solution evaporates, leaving vanadium oxide. These two compounds react to form bismuth vanadate, which is the compound we want. The product from the furnace looks like this, thus bringing us to the next important step, the etching step. The films are currently covered in excess vanadium oxide, so we need to place them in a 1 molar sodium hydroxide solution. that's capable of dissolving most of it off, so that we're left with pure bismuth vanadate films, which look like this. Again, to confirm the product, we needed to characterize the films. So we turned to X-ray diffraction once again. Here is the resulting plot for sample A. We recognize key peaks at 2 theta equals 18.9, 28.4, and 30.5. When comparing it to some literature source, the same one as before, looking at curve B this time, we could see that the peaks match very well once again, showing promise for our product. We then reinforced our characterization by looking at the film through an electron microscope. As you can see, our electron microscope picture looks similar to the one taken from literature, both of them confirming its nanoporous structure. So with this extra evidence, we can safely say that we have produced bismuth vanadate. The next part of our research was testing the bismuth vanadate films in a photoelectrochemical environment. I won't be talking about it in this presentation, but please refer to my research partner's poster by clicking on this Google link. By the end of this photoelectrochemical testing, we witnessed hydrogen bubbles being produced at the cathode, as you can see there, and with only UV light as the input. This really offers promise to the future in this field, and we really look forward to utilizing bismuth vanadate's potential. The field of photoelectrochemical water splitting, particularly research dealing with bismuth vanadate, has been looked at quite extensively in the literature. You'll be able to find a list of sources and journal articles on this slide. But other than that, I would like to thank you for making it through my slideshow presentation and have a good day.